Hi, I'm Jean. I present the paper Probabilistic Active Meta-Learning, which is joint work with Steindór and Marc. The idea of meta-learning is to learn a shared structure across related tasks. During training, most algorithms select tasks randomly, and we argue that this exhaustive exploration of the task domain is not efficient. As an example, suppose that each task consists of learning the dynamics of a vehicle, and we have already learned these three SUV-type vehicles. Now, learning another car won't help us to gain much new information. However, if we were to learn a motorcycle instead, we would significantly improve the model. In this paper, we will follow the idea of selecting training tasks based on previous experience. Let's have a closer look at our algorithm. PAML takes in a distribution or set of task descriptors from an underlying task domain, an active meta-learning model, a utility function for ranking candidate tasks, and as an hyperparameter, the number of initial tasks. We start by building the initial dataset, train our active meta model, and infer embeddings for each previously observed task. We can then rank candidate tasks in the latent space, and finally, after selecting the candidate task with the highest utility, we add the new task to the dataset. Now let's look at some example results. The key question we try to answer in the experiments is whether PAML speeds up meta-learning training. Therefore, in all experiments, we measure the model's predictive performance on a test task grid. The tasks here consist of learning the dynamics of simulated robotic environments. And in this particular experiment, PAML is given no access to explicit task parameters, but only to indirect task descriptors that consist of images of card pole systems with different lengths of the attached pendulum. In these plots, we see the model's predictive performance over the test task grid in terms of the negative log likelihood and root mean squared error after a certain number of tasks is added to the dataset. We see that the performance of the random baseline after 14 added tasks matches PAML's performance after only 7. This leads to a reduction in the number of added tasks of around 50% to achieve the same performance. To summarize, we proposed an active training task selection scheme in meta-learning to improve data efficiency by ranking candidate tasks in a latent space. Thank you so much for watching this video. A code implementation can be found on my GitHub profile.